just people tend to make mistakes. All right, so for this one, we have relative min. So let's do the first derivative test. So what rule are we gonna need for our first derivative here? Product rule. Okay, derivative of x minus 2 is 1. So I'm going to bring down my x minus 3 squared plus x minus 2 times the derivative there. I'm going to need chain rule. 2 times x minus 3 to the first times 1. All right, there's our first derivative. Now to find critical values, we set this equal to 0 or find where it's undefined. If I set this equal to 0, I kind of would need to like multiply all this back out and refactor it so I can find the critical values. But there's actually something else we could do that might be a little bit faster. Notice we have an x minus 3 in both of these terms. Let's factor out an x minus 3. When we factor out an x minus 3 from this first term, we'll still have another x minus 3, right? Plus, what are we going to have left from this second term? 2 times x minus 2. Let's just make it, oh, why did I close the parentheses? Oops, eraser. I didn't mean to put that there. I'm going to go ahead and make it 2x minus 4. Now we can just like combine like terms here, and then we'll already have it in factored form. So we have x minus 3 times 3x minus 7 equals 0. All right, so my critical values are 3 and 7/3. Let's put that on the sign line. Let's see, 7/3 is like 2 and some change, so that one would come first, and then 3. To fill out our sign line, we're gonna plug in points that are in between each of these intervals, or if we're smart about it, we can think about it. This derivative here, if I were to multiply it out, is 3x squared, right? So it looks like this. I know it starts high and ends high, so I know these are plus. And what's going to happen at 7/3? Are we going to cross or bounce? And we're going to cross. So plus minus plus. All right, what are we trying to find? A value of x where there is a relative minimum. Do we have one? Yep, at 3. So x equals 3. It doesn't say justify, but I'm going to justify. Because y prime goes from negative to positive. All right, question number 2. Suppose g of 3 equals 7, g prime of 3 equals 0, g double prime of 3 equals negative 8. Describe the point 3, 7. What's happening there? This g prime of 3 equals 0 tells me it's one of these two situations. So the second derivative being negative 8 tells me what? It's concave down, so that means it's a relative max. That's the second derivative test right there. Relative max because g prime of 3 equals 0 and g double prime of 3 is less than 0. That's all you gotta write for your justification. All right, one last warm-up question. We have a table of values. We've got x, f prime of x, and f double prime of x. Which of the following statements are true? F has neither a relative min nor a relative max at x equals 2. Let's look at x equals 2. All right, first derivative is 0. So it is one of these situations. All right, what about the second derivative being negative? What does that mean? Concave down, so we have a relative max. So it is not true. Oh, but that second one is true. Is there a relative max at x equals 8? No. The first derivative is 0, but the second derivative is positive, so it's a relative min. So it is B. And that is definitely how you'll see the second derivative come up. Second derivative test come up on the AP exam. All right, let's do one problem from start to finish. That's what our notes are gonna be today. And I wrote on the board over here, these are all of the characteristics you're gonna be asked. Some of these we're gonna use calculus to figure out what they are and to justify, and some of them are things you should already know how to do. So we haven't talked about domain yet, but you are gonna be asked for the domain, the range, intercepts, asymptotes, all that good stuff. The very first thing I want you to do is look at the function and say, do I already know what it looks like? Do you know what this graph should look like somewhat? It's a cubic, right? So isn't it gonna look like that? Start there, because then you know if you're doing things correct along the way, you're checking at the end, especially if you get like a rational function, those vertical asymptotes, if you just start following a process, you might make mistakes. So I know it should look like that. So that means I already know what the domain is. What is the domain? Negative infinity to infinity. There we go. It goes all the way to the left and all the way to the right. Intercepts. You can always find a y-intercept. How do I find a y-intercept given an equation? Plug in 0 for x. So what do I get when I plug in 0? 1. Sometimes you may be able to find x-intercepts if it's something that is factorable. Or if it's, remember I said those 5 numbers, check -2, -1, 0, 1, 2, check those 5 numbers. If it's one of those values, then I would also expect you to graph the x-intercepts. So what we're doing for x-intercept is plugging in a 0 for y. So I know I don't know how to factor that. So next I'm gonna run through those 5 numbers real quick. We already plugged in 0. I know that didn't give me 0. What about if we plug in 1? Would that work? No. What about plugging in 2? No, 2's not going to work either. Does -1 or -2 work? Let's see, -2 cubed would be -8. And then -2 squared is 4 times -3 is -12. Nope, not gonna give me 0. Did -1 work? No. Okay, so I'm not gonna ask you to find an x-intercept if it's not something that's factorable or one of those 5 numbers, so we're gonna skip it and move on. Does this function have any asymptotes? No. What types of functions have asymptotes? Rational. Anything else? And what? Exponential and log. Perfect. Okay, I'm going to need this space in a second. These are the next 4 things we're going to do. Increase, decrease, relative extrema, concavity, point of inflection. All of this we're going to use calculus for. The first 2, we're going to use the first derivative. The second 2, we're going to use the second derivative and create our sign lines. All right, so I'm going to go back because I need some space to work here. All right, first derivative, y prime equals 3x squared minus 6x. Get our critical values, so set it equal to 0. Let's see, factor out a 3x. All right, so my critical values are 0 and 2. Let's make a sign line. So I'm putting 0 and 2 on my sign line. Do we know what the signs are going to be? It's another 3x squared. So it's going to start high and end high. What's going to happen in the middle? Yep, minus. Okay? All right, so can we do intervals of increase and decrease? It's going to be increasing from negative infinity to 0 and 2 to infinity. All right, increase. Negative infinity to 0, union 2 to infinity. What's my justification for that? Yep, and they called it y, so I'm going to call it y prime is greater than 0. And it was decreasing in the middle there, 0 to 2. Because y prime is less than 0. Do we have any relative extrema? the y values from the original function. So what do I get when I plug in 0? Oh, didn't we already do that? 0, 1. All right, and then someone tell me what you get when you plug in 2. Relative max at 0, 1. Relative min at 2. What is it? Let's see. 8 minus 12 plus 1, so -3. Alright, and what's my justification for these ones? Relative max, because y prime goes from positive to negative, and relative min because y prime goes from negative to positive. Alright, for the second two, we're going to use the second derivative. So I'm going to go back to my previous screen. Which one do you think would be easier to take the second derivative of? The non-factored or factored version? I think non-factored, because we can just do power rule. So 6x minus 6. Alright, so set that equal to 0. So my critical value for the second derivative, x equals 1. Isn't it nice with polynomials, the more you take the derivative, the simpler it becomes? Alright, so 1 for my sine line. Plug in values, or think about the end behavior of a linear function. What's this going to be? Negative, positive. 6x would go like this, so I know it's going to start low and high. Alright, so concave down, then switches to concave up. Alright, so concave down from negative infinity to 1 because y double prime is less than 0. Concave up 1 to infinity because y double prime is greater than 0. Any points of inflection? Yep, y double prime changed sign, so it's at 1, we gotta plug in 1. Alright, what do we get when we plug in 1? -1. Is what? Yes. Yep, for this and this, you're plugging into the original. Because these are actual points on the graph. Alright, we've done everything. Now we can actually graph. So, here is the, oh, skip that. Here's the order I like to do things in. I first go through and put any points we actually found on the graph. If there are any asymptotes, you will graph that next. Then we're just going to make all the pieces fit. So a lot of times if you know what the function looks like, it's going to be real simple to draw it. If you don't know what it looks like, you need to look and say, okay, it's increasing, then it switches to decreasing, then it goes to increasing again. I got to make sure it matches all of that. All right, so what were my points? I know we had a y-intercept at 0, 1. A relative max is also at 0, 1, 2, -3, and 1, -1. Let me put those on the graph. 0, 1, 2, -3, 1, -1. All right, not a whole lot to go off of. I got 3 points. The next thing I like to do is for the relative max or min, I like to draw a little like max or min. So this was a relative max. So I'm literally just going to draw a little like this thing, whatever you want to call that. And at relative min down here, I'm going to draw a little like this thing. So now I'm like, okay, I can start to picture it now. What was happening at 1, -1? Point of inflection. Okay, so that is probably the only thing you've never graphed before is concavity. So here's what I would suggest. We know it's going to like start here and come up like that, right? So I'm just going to go ahead and start to draw it. So I know it's going to start down here. I'm going to come up to this, come back down, and I'm going to stop at that point of inflection for a second. And I'm just going to visually say, did I draw that so that whole side looks concave down? Yeah, I think so. Now I'm going to stop and say, okay, I have to switch to concave up, so I want to make sure it's like more like this. Whoop. There we go. and see how close we are to the actual graph. That's pretty similar, pretty close. Okay, so when you guys were graphing, you know, way back in Algebra 1, you start graphing, you like had a bunch of little points. I don't know how they taught you to graph back then. In Algebra 2, I know we switched to saying, all right, all I care about is x-intercepts, y-intercepts, and behavior, that type of thing. Now it's a little bit more specific, so I want to be able to tell where the concavity changes. It should be really clear where it's increasing, decreasing, all of that stuff. So we should be fairly close to the actual graph. I'm changing up the homework for tonight, so it's not actually the worksheet that's next in your packet. I want you to go ahead and grab your homework packets and go to worksheet 3 for a second. Worksheet 3. It was 4 problems. I gave you the function, first derivative and second derivative, and you had to do all the characteristics. Your homework for tonight is to graph those 4 functions. So you've actually already done all the hard work. All you have to do is now take all that information, check your answers before you start graphing, because if you never check the answers, your graphs are going to be off, and then graph them. And I have graph paper up here. I'll let you guys come get if you want. But I mean, the first 2 are cubic, so you should already be like, okay, I know what that looks like. The second 2, they're kind of weird. We've got sine plus cosine, so it's probably some type of cyclical looking thing, but I don't know. Does it look like sine? Does it look like cosine? Does it look different? And then same with number 4. It's x squared minus x minus log x. It's not really quadratic. It might, some of it might look quadratic, but that log is going to change things up. So there's no answer key for this because you can just graph it in your graphing calculator and see how close you are. Okay? But that is your homework for tonight. Yeah.
What do you want to do? What do you want us to do last week?
I mean, well, it needs to look like the actual graph, but you're going to use all your characteristics to help figure that out.
Well, because like we're just going to have that.
Well, like it. So instead of when we went to go graph this, I was like, well, I already know it looks like that. But if I didn't know what a cubic looked like, then I would have to go back to this and say, okay, well, it looks like it started out increasing, so I know I need to start low and it needs to be going up. And then it switched to decreasing, then it switched to increasing. So then you start to get it in your brain of what it looks like.
Are we going to get any like sine effects?
You might.